Yes.
Yes.
Oh, okay, perfect. All right, good. And I will need to connect for a moment through my iPad because I have some notes there. Then we'll start. 1 second. Mm-mm. No. Okay, excellent. Mhm. Okay, I think we are good. I have another question to ask you. Do you hear a little echo or it's not coming through?
Yes.
You do? Okay. Well, let me do
A
something.
little bit.
Yeah, a little bit is coming. Yeah, I know. Okay. Can you hear me? Sorry. Okay, can you hear me now?
Yes.
Okay, perfect. So I just changed the voice through my iPad and the picture, the video from my other computer. Okay, so before we start today, we are week 2 and we are Friday. So today we're talking about vector calculus. I would like to make a couple of comments, if I may, before we start. So first of all, welcome to everyone. The comments I would like to make is on the basis of some of my observations, and I just wanted to clarify a little bit. So again, um, look at the use the main page, like the home page, as your guide. Everything that we have, I place there. The most recent list of things that we have done or we will do is on the main page. The syllabus, it's always something we put up there in the beginning of the class or before the class starts, and it's not necessarily updated all the time. It just gives a description approximately good, because we try always to follow it, but not perfectly. It gives a description of what we plan to do in the class, but is not necessarily the most accurate schedule for the class, because as you can imagine, the class is develops organically on the basis of the needs and what we need to cover. And sometimes we may have to slow down, sometimes we may have to skip some things, sometimes we have to do things. The syllabus is not supposed to be a direct reflection of what is happening in class. That you find it on the home page, number 1. So also for Zoom, as I was talking with your colleague, the most accurate times for Zoom are here. You click on Zoom and you see all the times that are perfectly developed for your class. For example, on the syllabus says the office hours is like right after the class or at the same day. But here we decided to put office hours on a Sunday, 1 to 3, in the middle of the day, as most of you requested. So students who are trying to solve homework that day have access to me. So you follow this, you look at the times, the days of the week, and yeah, then you connect them.
I was
Then
wondering
go,
if we can, ask,
yes.
like vote if we can move it like on Sunday 1 or 2 hours.
Is that USM?
Yes, that is.
I can do this, but do you want me to do a polling?
Yeah, that's okay.
Polling. The question. Okay. Let me see. When would you like your Sunday? Would you like your Sunday office hours? I will give 3, 10 to 1, 1, 2, 3, or 3 to 5 p.m. Okay, Paul, and let me see. Save answers. Single choice.
You can copy and paste the times into the answers.
What's that?
You should copy and paste the times into the answers.
Thank you, thank you. 1, 2. How do they do that?
Also, Professor, you may need to
Okay.
select multiple choice instead of single choice.
Single choice. I make it multiple. Okay. And then I save it and send it.
The second answer choice needs to be revised. It's a duplicate of the first answer choice.
Sorry. Yep. That's what happens if you don't know exactly how to use it. So 1, 2, 3. Okay. Now what do I do? I do save and you see it. What do you know?
You need to
from
change,
here?
Dr. Katahi, you need to change
Yes.
it on the second answer choice as well. Like you changed it in the question, but it's not changed in the, like, yeah, there.
Yes, thank you. Thank you. And then what do I do? Do I save it? How do you see it?
Yeah, I think you can just hit save.
Oh. Okay. Launch poll. No, there it is. All right. So you see that while I'm continuing. You do it in real time so we can see it. Please make sure that you all vote because we're going to make a change. For those who would like to go 10 to 1, where would you prefer? There are about 12 people. Just tell me. Between 1 to 3 and 3 to 5.
Yeah, I guess I prefer 1 to 3.
Anybody else?
I
Same, I
one
would
to
prefer
3.
from 1 to 3.
1 to 3. Raise hands. Can you raise hands so I can see? Let's see.
How do you raise hands?
All right. Well,
It's in the
you know,
participants tab.
participants. Wait. Oh my God. Sorry, participants tab. Yes. Okay, 1, 2, 3. Let me see how many. Okay, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 want from 1 to 3. The raise hands. Okay. All right. So let's see. We are 1 to 3. That's what we're gonna do. Okay. Any questions about that? All right. So now that we settled this, let's go to where was I? I want to go there. Okay, so we are home now. Okay, so we are here. The other comment I wanted to make is the following, that this class is an online class, and it means it's not asynchronous, it's a synchronous online class. So that means that if you are not in class during the hours we are teaching it, then you will have to have access to the material. Usually what I do is to record the lectures, and I'm gonna make sure that I record this lecture. Do you see the recording?
Yes.
Okay, perfect. So the lectures should be recorded. I have set the Zoom like this. And what I normally do is that I download the Zoom, I do some editing to remove the dead time or time that is, because otherwise it's extremely long. And then after the editing, I upload it to YouTube, and then I connect that so you have access to it from wherever. However, that takes time. So I cannot do this immediately after class or immediately after the end of both lectures I'm giving. Usually it takes about a day by the time, because I have other things as a faculty member to do. So it's always my time is very busy. But in any case, I try within a day to place them up. I understand that you are very anxious to see the lecture, but please do not try to put pressure on me, because I'm already pressured from all different directions to do things, and I try to do my best, but do not pressure me to try to do it as soon as you are available to see it. We will have to try to accommodate each other, because this is very intense. It requires a lot of preparation time on my behalf, and it requires a lot of time on your behalf too. I don't de-emphasize how much time it requires to do an online class for people like me and you that have different expectations, be in the classroom and interacting and do different things. But I think to be able to do this well, we have to help each other. And by helping each other, that means remind me if I have been delinquent in something, because I will do it immediately. I'm a human being, I forget sometimes. But also be understanding of the times that I have available. That's number one comment that I would like to make. And then please, if for some reason you think that what I'm suggesting may not necessarily be reasonable, let me know, call me, email me, and we'll do that. Number two, do not email me through Canvas. because Canvas does not allow me, even if I see your emails that come to me and I check my email everywhere from my iPhone and everything, I cannot email you back unless I get on Canvas, which is very inconvenient if I am on my cell phone and I'm not in front of my computer to do this. So use my email, which is available under information. Is katehi@tamu.edu, and email me directly, because then I will be able to respond to you immediately as opposed to waiting until I get on Canvas and so forth. That's 2. Number 3, office hours. Office hours are, what I'm doing in office hours is to do 2 things: help you with comments, with issues, specifically with topics, rather. If you come, for example, and say, I don't understand this topic, then I will repeat the particular, I will give you some examples. Sometimes we use office hours to do reviews, as you will see. And most of the time, office hours are for you to come and ask me questions so you can solve your homework or your quiz. Please do not come to office hours so I can solve your problems. Because if I help you so much in your homework that I feel that I have solved the problem for your homework, then the question for me, the ethical question for me, is what grade am I going to give you? And that places me in a very difficult position. It's not only ethical on my end to ask, does this student deserve this grade if, since I solved 90% of the problem? But also the question that I have is ethical for whether I'm violating my own ethics, but also it's an issue of fairness to other students. So come to your homework, to our office hours, prepared to ask me not how to solve the particular problem, but to ask me questions that will help you solve the problem. And so there is a difference between tutoring and between office hours. Tutoring is where somebody comes with you and they take you through all steps of a homework. But I'm not going to do that because I also have to grade. I am not only helping you, but I have to assess your learning. So if I have to start doing things for you as a tutor, then I default, in fact, in my capability, if you like, to do an accurate assessment of what you know. So I wanted to say, read your homework well. Read it carefully, because a lot of times you read it very quickly. I know you're very busy, and I understand that, but read your homework carefully and try to understand which parts are difficult, because sometimes you're asking me questions which are obvious. And to me, it tells me 2 things, because I know how good you are, how smart you are, and how hard you have worked so far. So I put this aside. What it means is that you are missing a lot of information that would help you solve the problem, because probably you have not spent enough time thinking about it. So in any case, if I see that there are some deficiencies across the board, then I will do review sessions where I'm going to solve other problems or other examples to help you. So that's what I wanted to give you some guidance in that regard. Any questions or comments in regards to these 3 things that I mentioned? Okay, I hear none. So today we're going to go to vector calculus. So I'm going to stop share from here, and I will share my screen from here. And I will go to my notes that I have on Notability. And are not those the ones that I would like to share with you, but these are the ones. Okay. Now, today, And I have to remind you that we are doing a review. These topics are not topics that we are supposed to cover as new topics in this class, but they are topics that we review so then we can move forward. Now, you have seen some of these, but we will talk a little more, and specifically what I wanted to say is that you will see them over and over again throughout the class. So at the end, you're going to become very familiar. But there are some peculiarities, especially when we come to these operators, as we call them. And these are important operators because they give us important information. And that's what I would try to share with you, that information, to try to appreciate the information these operators give. And that's why we are using them, because otherwise we would not use math that was useless, all right, or would add complexity for no reason. So first of all, this delta that you see here, the inverse delta, all right, so we show it like this. This is an operator. This operator is a vector. And this vector has three components if we are in a three-dimensional system. It's a space operator. In other words, it applies to physical space. So 3 dimensions, X, Y, and Z, if you are in a Cartesian system. How could you, in simple yet mathematical words, explain what this operator does? Let's assume that our space was one-dimensional, that we had only the X direction, as you can see from here. Let's assume that we have only the X direction. And we live in one-dimensional space, so the meaning of the vector, it would not be useful. All right, so if we were to be one-dimensional species, animals, then we would live in one-dimensional space. What would that be in that one-dimensional space? What this operator would mean?
Derivative.
Derivative. So this operator will mean derivative. Why derivatives are important? Why did we even use them? Why did we even introduce them? Just to make life difficult? No. Why are derivatives important? Why do you think? What would derivatives show?
They describe rates of change.
Yes, a derivative describes change. A derivative for something that does not change, let's assume we are still in one dimension, all right, to simplify things. A derivative, theta x, for example, if we were in the X dimension, of a function or of another entity that does not change is 0. And the derivative gets a non-zero value only in places where there is a change. Why is that important? Do you know, as a matter of fact, an animal that only sees change? Do you know of a species that, of an insect, rather, to help you? Do you know of an insect that sees only change? And that's why it's very difficult to catch it. The fly. Do you know that the fly sees only change? That's why it's very difficult to catch a fly. You have to be extremely fast. Faster than if it takes for a fly to see that the changing is happening. And it's amazing, isn't it? That's how flies see. That's how they were able as a species to evolve to protect themselves. Why is that important for that little fly to protect itself? And why was it like the evolution changed it in that direction, so it does not see very many other things, but only when change happens? Because the brain is small, does not have many neurons, and if the brain is small, cannot process all the information. So for example, if the fly was looking at a tree and then nothing is moving, okay, why would the fly worry about how the tree looks like? Maybe it likes zero, nothing. It likes to see nothing. But when there is something is moving and that little motion is dangerous, then it sees that. And because the brain does not worry about seeing everything else, but it sees only that motion, then it can process it extremely fast in real time. That is how it works. And that's why derivatives are important to us. Because when it comes to understanding the change from a status quo, let's assume that we are in some steady situation, in equilibrium, for example, where nothing changes at equilibrium. And from there, there is a point where something happens, then that derivative is going to show the place immediately where that change happens, as small as this change may be. And why is that? Why do you think even a small, teeny change was going to create a big derivative? Let me just show you that. Let's assume that we are in the one-dimensional space and we have a function that looks like this. All right? And let's assume that we record the value of this function at every time. And let's assume that this value is 5. Okay? And then what happens all of a sudden, and I will do it with red, that's 5. Therefore, let me also show you the system so you can appreciate what I'm talking about. So this is your coordinate system. This is x. This is the value. Only one dimension, all right? Only the value is there. And the value is 5. And then all of a sudden, at some point, we see this. The function changes at that point by teeny bit. If this is 5, then that will be a 5.1. Okay. Now, if I were to look at this and it's so small, I could even neglect it. I may not even see this little change if I am to be even more specific. Let's make it smaller here. There. Let's assume that if I were observing everything, I may miss it. But what happens if I look at the derivative? What happens if I plot the derivative here? All right, so this is the value, this is the derivative. What would you see if I plot the derivative? I will plot it with blue. Can somebody tell me? Or do you want me? I can do it. It's gonna be 0, 0, 0, 0. And then what is gonna be here? What is the derivative there when it makes an immediate small change? It's gonna be big. And it can be a lot bigger than the value. It's gonna look like this. It can be even bigger depending on how the change happens. If I were to, so the derivative will look like this, and that can be the value of 10 for the derivative. Why is that? Because if I make this here bigger, if I increase the view of this, it can look like that. 5 and a glitch. All right, and that glitch, if this is 5, that glitch could be 5.1. So tell me now, how much the derivative of a glitch like this is? Do you know what happens, how big the derivative is for something that changes like that? It's infinite. Do you remember from the derivatives, when you have a function like this, how much is the derivative here? It goes from 0 to a number. So the derivative within time 0. So the derivative of a step function like this is theoretically infinite. Practically is like a glitch that is very high. In the derivative can be much higher than the glitch itself. So if I want to see small changes, because eventually small changes may lead to bigger changes, like a snowball, then I would like to look at the derivatives. The derivatives are very important, therefore, in understanding what is happening. Or when I have sensors, that I'm going to sense whatever, anything. When, for example, we would like to look to understand seismic events, and usually it's a very noisy environment, as you know, when you record seismic events. Like the earth is like moving, everything is moving. So you always get a very noisy reading, as you have seen from seismograms. And then all of a sudden, if there is a little glitch that goes higher from the noise, if you try to develop the derivative of that and remove with some techniques white noise and so forth, you will see a huge difference in the derivative. And you know that in that particular point, you had an event. So that's why it's so important in electromagnetics too, to be able to have the notion of the derivative embedded in your understanding of forces and fields. Because sometimes a small change may be the beginning of a much bigger change. And a lot of times that in dynamic systems that do not have some form of feedback, as you will know from your systems work, a small change may lead into a much bigger one. All right, so the standing change is very important. Now, since we don't live in a one-dimensional system, but we live in three-dimensional systems, then the gradient operator is, which we introduce, is a vector and has these three components. Okay, so now what I would like to do and what I have here, and I have put it, whatever I put in my notes, in the form of a, like in a box, that implies that this is important. So, and I don't know whether I have any questions. Okay. So what I would like you to do here, to remember this, there are in the book, and you have to familiarize yourself with the book so you can find them. Put some stickers there so you know where to find those relationships, because we will use them, as you will see in some examples. So in cylindrical, in rectangular coordinates is here, number 1, rectangular coordinates. But then in cylindrical coordinates, I have it here. And then in spherical coordinates is here. All right. So you keep that in mind. Then I have an example here on how to calculate. I give you as an example a function in cylindrical coordinates. And I want you to find the, and I have to remove this one here. So I want you to find now the divergence, the gradient, excuse me, of this function. This is a scalar function. So we have gradient, we call it. The gradient of a scalar function is what? Is it a scalar, a vector, or a tensor? Remember this definition. What is the gradient of a scalar? Is a vector. Can you hear me?
Yes.
Yes, just I want to make sure
Yes, ma'am.
because yeah, thank you. Just want to make sure because sometimes okay, so the gradient of this is a vector, and then I write it because the function has been given to me in cylindrical coordinates. Then I'm writing the form of the gradient in cylindrical coordinates, and then I do the integrations. See? And then I plug in the integrations because now somebody has asked me to find the gradient in Cartesian coordinates. So here, what I eliminated, I will add it and say find the gradient of f in Cartesian coordinates. So this is what the problem is asking. Okay, so I do the integrations, I apply the gradient in this particular case directly in the cylindrical coordinate system, as you see here. And then after I solve the whole thing in cylindrical coordinates, now I'm gonna go and try to change it into Cartesian coordinates. And I use these formulas, which are also in your book. And in fact, I will also put those into a square, just to remind you that these are important functions. And then I look at those and I plug in, and here is the form of the gradient of this function in Cartesian coordinates. And why would I need to use it in Cartesian coordinates? Because possibly after I do that, maybe I have another gradient of another function and I need to work both of those, and each one of them are on separate cylindrical systems. So if I bring them together into one Cartesian coordinate, it's going to be easier for me to work with. So, but this is a simple mathematical exercise to see how you go from a cylindrical system to a Cartesian system, and you can do similar things with spherical. Any questions so far? Okay. Let me see. The divergence operator. So now the del is the inverse delta. And the del has the form of a vector. And as the vector applies, then we give it different names. So the del vector, when it applies to a scalar, is called the gradient of the scalar. When a del vector applies to a vector, it can apply to a vector in two different ways. All right? Because vector operations do not have like scalar products. In a vector operation, you can only do a multiplication in two different ways. You can do a dot product, or you can do a curl, which is like the cross product. So the dot product of the del operator on a vector is called the divergence. And when we have a dot product of the gradient on a vector, we call it also the divergence operator, which is like this one. The divergence operator is the del, but in a dot product. The del by itself on a scalar is called the gradient. All right, we just saw that. The del in a dot product operation is called the gradient, and it only applies to vectors. So if a del operator, which is a vector, is involved in a dot product with another vector, what is the result? The result is a scalar. All right, here. Why is that scalar important? because the difference between this scalar and the gradient is that the gradient separates the changes of a scalar function into the 3 dimensions. So since the gradient is a vector, like we show up here, since the gradient is a vector, what that says is that if I have a scalar function that is a function of multiple parameters, the gradient will show me individually how this scalar function varies in each of the 3 dimensions separately, and separates them by making them components of one other vector, the x, the y, and z component. But in the divergence, which applies to a vector, the divergence shows us the overall change of the vector. It shows us how the x vector changes along the x direction, the y vector along the y direction, and the z vector along the z direction, and sums the whole thing up. So it shows us really a change of a vector and how this change, this vector, if you like, derivative in that way, how it changes in the various points in space. And this divergence is extremely important. The divergence is a very important operation in vectors. And also, I show you here how the divergence writes for in the Cartesian system, in the cylindrical system, and in the spherical system. And also pay attention how you have to always be very careful how you deal when you go away from the Cartesian into cylindrical and spherical. Pay attention to what you have inside the parentheses. So I have to ask you a question here. Do you know what this guy, the question is, do you know one particular thing that we do? Forget the flies and what the flies see. Do you know of one particular that we all have done in our whole life that shows us writing down the divergence or the derivative rather than the function? What is it one thing we do every day that really follows that rule of the divergence? How do we apply that without knowing that we've ever applied this, where we show the divergence instead of showing a function? That's a question. So to answer that question, which may not necessarily be very easy, even if it's obvious when I tell you, I'll show you this. Do you remember where this is from? This is a very famous painting. Who will tell me if you have seen that from your arts classes? That is what, you remember?
The creation of Adam.
Yes, thank you. But Michelangelo, yes, very famous. Now, when artists like him were painting on walls, how did they paint? Do you think that they went there and they had everything in their head and then they put it down all at once and then they put the colors all over them and they were able to do it? No. For them, that kind of painting is what we do today with research in electronics. It was a new thing for their time. It was an advanced technique. And they were researching it at the same time they were making it. So how did they come down when Michelangelo decided to do this hand movement? That without seeing whose hand is, you can tell me which hand belongs to whom. So which hand belongs to whom? The left belongs to God. All right? And the other one shows the stress of trying to connect. But in any case, how did he get there? Look at this. Do you see that? These are his individual's drawings. Well, he tried different hands. But did you think that he colored them? Did you think that he painted them to try them? Of course not. It would take him the same amount of time as he did the painting to try the same way the various hands positions. So what did he do? He decided to draw. Eventually he put the shades and everything. But how do you do sketches? How would he do a sketch? He would start with the main lines, all right? So for example, I'm not a good drawer. I'm not good in drawing, but I will tell you, he started with this hand here. Most probably I will draw over and then remove it. Most probably he started with this. With this. All right? And nothing else in between. What is this doing? What is he doing there when he did the sketch? He practically drew the derivative. Do you see that? He practically found where there is a major change in the color, in the optics that we see in the picture. And instead of drawing the whole picture and all the colors and variations, he drew the place where the derivative was the highest. So when we draw sketches, that's what we do. And why is it when we draw a sketch, when we try, I'm not very good, I'm telling you, in drawing, but when we do this for a person, what do I do here? I only design the places where the derivative, that looks like an ancient Christian creature. This is, I only draw the places where the derivative is the highest. Do you see that? And why do I do this? Because it's easier for me to do that. I have to spend a lot less time to see the graphic without investing too much time for something I can then remove if I don't like. So do you see how we do this already? Our brain knows that. We have done this for years without knowing that what we really write down is the derivative of a function. If we could take these two hands and create a function out of it, then, and if I were to develop from there a derivative, that's how it was going to look like. If I were to take different values of the derivative, this is what I would get. So now you can see that how we do things, it's not like that mathematics have come out to us from nothing, and we developed mathematics really to make our life difficult. Mathematics have been derived out of our own observations and then have helped us give meaning to things that we either have done for millions of years or thousands for the human species, or we're doing recently. But so that's what I wanted to tell you, that you've been doing this. Now, another thing, the final thing here is the curl operator. The curl operator is in 3 dimensions, and I don't have to say more than that because we're going to come to it. But the final thing I'm going to say, and I apologize for being a little late in this, but since we started a little late the lecture, I need a few more minutes. The most important thing you need to keep in mind is how we use those to classify fields. Because eventually, that's why we use these operators in electromagnetics. We use them to classify a field. All right, so remember that and try to also spend a little more time, because I'm going to give you a quiz based on this. The quiz I'm going to give you today, which you're going to have to do from today until Monday morning, is going to be based on this exactly material. So first of all, a field, a vector field that looks like this, it goes in one direction and is constant, has neither of the divergence or the curl. So it's called solenoid. It flows and it does not mix with anything else. All right. This field, however, that you have seen mostly from like when a charge creates a force, all right, if the charge is here at the center, then you have a field like this. That field does not have a zero divergence, but has a zero curl. So it's not a solenoid because its divergence is not zero, but is called irrational. Irrotational, excuse me, not irrational, irrotational. So in other words, if the curl is, oh, I don't read the chat. Yes, please do not ask me because I cannot teach and read the chat unless I stop. So if you can help each other is fine, but I will read it at the end. All right, so it's irrotational. When the curl is not zero, it shows some kind of rotation. When the divergence is not zero, it shows some kind of a flow all in one direction, okay? So here, what do you see? You see a flow, but there is no mix of lines. So it's going around, and what happens in this particular one, it's both a solenoid, but also
Excuse me, Professor, I think you muted yourself.
Professor, we can't hear you.
She's not muted, she has two mics open, so she probably crashed.
can you guys hear me?
Yes. Yes.
Yes, ma'am.
Yes or no?
We
Yes,
can hear
ma'am.
you now.
I can hear you.
Now we can.
Can anybody hear me?
We can.
Yes, ma'am, we can hear you.
Yes.
Hear you.
Can you hear me?
Yes.
Could you hear me before?
No.
No. Okay. All right. So we'll move to this one now. For how long have you not been able to hear me?
Maybe 1 minute, 2 minutes.
2 minutes. Okay.
You began talking about the curl and then you suddenly
Okay.
were silent.
Okay. So for something happened here. Okay. So you can hear me now, though. All right. Yes.
Yes.
Okay. So I was here. So I said this one. So the first one is like a solenoid. All right. So it goes on a flow. It does not mix and it goes on one line. and both the divergence and the curl are 0. So solenoid, when the divergence is 0 and the curl is 0, so it's a solenoid without rotation. When the divergence is not 0, but the curl is 0, is not a solenoid, but does not have rotation. It's called irrotational, if there is a word like that. Then here, if the solenoid is, so there is something else. Let me see, one moment. Did you see that I stopped sharing here? You don't see that, isn't it?
We still can see the screen.
Yeah, but it's the frozen, it's a frozen screen. It does not matter. For some reason, I don't know what happened here. Okay, that's all right. This is the last one of our discussion. So in any case, it happened at the end. So this one, when you see you see when I'm turning, do you see that? Well, probably. No, it's okay. The second one, so the B is the one that does not have a rotation. Oh, there it is. So now, see, now it worked. Join the meeting. One moment. This is gonna be here. I will share screen and do this here. Okay, so one moment, if you can bear with me for a moment because something happened here. Close. Okay, there I need to go here rather. Howdy. Go. I think Howdy got me out of the system. That was the last thing that I needed. Okay, 4:30. Join. Right. All right, so I'm going here. And share screen. 1 second. Okay, that's where we are. What I was saying is that the first one is a solenoid. The second one that is not a solenoid but has rotation. Excuse me, does not have rotation. Is not a solenoid and does not have rotation, all right? So the divergence is not 0, which makes it a solenoid if it is 0. But the curl is 0, which means that does not have a rotation. Usually if the curl is 0, it's irrotational as we call it. If the divergence is 0, it's solenoid. So the second one is not a solenoid, but does not have a rotation. The third one is a solenoid, but it is, it has a rotation. So you see that the lines do not mix, they all go. So for example, if I had a particle here, this one, the red one, will always stay in the inner circle, and the dark one will always stay in the outer circle. So it moves like a solenoid, but it has a rotation, all right? Because the curl is not 0. And then here, this is neither a solenoid and has a rotation. So it's neither a solenoid nor irrotational.
It's 9 o'clock.
But it would say it's neither, it's not a solenoid, but it has a rotation. Why is that? Because if I have a particle here, which is red, after a little bit of time, the particle is going to be down here because it's moving in that direction. And if I have another particle, which is here, after some time, this particle is going to be here. So what you see is that the lines are mixing up, but they are moving around. So it's not a solenoid, but has a rotation. So whenever you see movement around like a circle, it is a rotational field. And if it's a rotational field, then the curl is non-zero. If the divergence is zero, that means that it moves as a solenoid. And it can move in a straight line or it can move in a circle. So with that, we are going to stop here. And please use this last, and there is a section in the book that is called field classification. And go and read that section of the book before you do the quiz. And for the quiz, I will, in fact, I will show you what the quiz is here. And go here. And we go quizzes and quiz 2. And in quiz 2, I give you these fields and I ask you what type of fields they are. In fact, I ask you to identify the right answer. So I will assign it. And you will have until Monday to do it, but read my notes and look at how they curl and then divergence are in different coordinate systems, because obviously here I give you different coordinate systems, and look at how you classify a field, and that is going to help you do the quiz. Okay, so that's going to be for Monday. You should not spend enough time. If you have this information next to you, you will do it very quickly.
Dr. Katahi,
Yes.
would you be able to post your handwritten notes that you went over today on Canvas?
Yes, absolutely.
Thank you.
Yes, I will do this right now, as a matter of fact. Post them right now so I don't forget. Yes. Any questions?
Yes, ma'am. Which sections of the book should we be reading according to lecture?
Now, according to lecture, let me go back to here. All right, it says in the top of the week, do you see that?
Yes, ma'am.
Calculus and representation of the book, it shows the sections of the book.
Okay, perfect. Thank you.
You're welcome. Any other questions? Okay, I will upload this right now. Thank you.